Alright, so on your foldable, we folded in each corner so that we have a graphs corner, a tables corner, an equations corner, and a scenarios corner. So what we're going to do today is we're going to write down a couple of notes on how we can identify a linear function from each of these four descriptions. So I'm going to start with graphs. So I'm going to start with graphs. I'm just going to I'm going to draw a dotted line on my fold so that y'all can see where my paper is. See, maybe if I darken this a bit. There we go. Is that better? Much better than in the back? All right. So on graphs, how I can identify a linear function in a graph is when I graph it and I just look at it with my eyes, I'm going to see a straight line. I'm going to see a straight line. I'm going to draw 4 examples of a linear function that has been graphed. Alright, so if I have a linear function that looks something like this, it's pointing down and to the left and up and to the right. It has a positive slope. Alright. Another example. If I'm pointing up to the left and down to the right, what kind of slope is that? Negative. If I draw a line straight up and down, this one's a vertical line, and that's an undefined slope, right? Vertical line. If I draw a line straight across, what kind of slope is that? It's a zero slope and it's a horizontal line. Beautiful. That was beautiful teamwork. Alright, so a graph, to identify a linear function from a graph, is it looks like a line. That's it. It looks like a straight line. Is that okay? Alright. Let's take a look at tables. Can we turn clockwise to tables next? I'm going to fold graphs back. I'm going to turn clockwise to tables. There we go. So under tables, my reminder for a table is that I have a constant rate of change for all of the points. I'm going to write that down. Constant rate of change for all points. Alright, and I'm going to do some examples and some non-examples. So let's start with an example. So an example would be, let's do a table with the points 1, 5, 2, 10, 3, 15. So to check to see if these points all have the same rate of change, I'm going to compare. So from 1 to 2, what do I do? Add 1. Beautiful. From 5 to 10, what do we do? Add 5. So if all of my other points have the same rate of change, then we have a constant rate, then we have a line. Okay? So from 2 to 3, plus 1. From 10 to 15, plus 5. Okay? Let's do another example. X and Y. Let's see, I've got 4, 7, 8, 7, 12, 7. All right. So from 4 to 8, what's my change? Plus 4. From 7 to 7, what's my change? Plus 0, right? From 8 to 12, what's my change? Plus 4. 7 to 7, what's my change? Plus 0. So do we have linear function? Yes, because all of my rates of change are the same. So I have the same changes with my x's, same changes with my y's. And we're going to talk a little more about those changes when we get to slope in about 2 weeks. Okay? So let's do some non-examples. So a non-example would be, x, y, I'm going to have 2, 2, 1, 4, 4, 6, 9. So what's my increase from 2 to 4? Plus 2. What's my increase from 1 to 4? Plus 3. Okay? So from 4 to 6, my increase is plus 2. So 4 to 9 should be plus 3 also, right? So what is 4 to 9? Plus 5. So right there, I want to circle it, highlight it, bring attention to it. Because these are not the same, that makes this nonlinear. Is that okay? And like I said, we're going to come back to this idea, this constant rate of change. Or another way to say rate of change is slope, right? We're going to come back to this idea in a few weeks. But I want you to know that we can tell from a table if all of my changes are the same, then we have a line. All right, let's take a look at equations. I like the equations one. The equations one is fun. So my equations, my number one rule for a linear is I have no exponents. No exponents allowed. So let's do some examples and non-examples like we did before. So some examples would be y equals 3x plus 5. See, 2x minus 7y equals 9. Oh, sorry. see. Ooh, what about x equals 3? Do I even have to have a y? No, I could have a vertical line, right? That's still a line. What about y equals -8? Does that work? No exponents? All right, so let's do some non-examples. So if I have like y equals x squared plus 4. See the exponent? That's squared. Makes it not a function, not a linear function. Or if I have x plus y cubed equals 5. Or even, and we're going to see this one later this year, y equals 2 to the x power. See, your exponent doesn't have to be a number, it can be a variable. So all of those are examples of nonlinear functions. Scenarios, yes, that's going to be our last one. All right, last window in our foldable, the scenarios. So what we need for a scenario to be linear is the units in my scenario all have to be to the first power. So I'm going to say all units are to the first power. We have a constant slope. And I like these examples versus non-examples, so we're going to do those again. Let's see, I'm going to go with green. So scenarios are like real-world examples, right? So a real-world example that I can think of that is linear would be a perimeter. All right. Because perimeter, if I add up all the sides of a triangle, right? Length plus length plus length, that's going to give me length. My unit is to the first power, right? What about area? Is that going to be to the first power? No, because length times width, if I have inches times inches, that's inches squared, right? So can you all think of any other examples or non-examples of real-world scenarios? What about volume? Would volume be with perimeter, example or non-example? Non-example. Marcus, what do you got? No. I bet it's a great idea.
Well, if it doesn't have a constant slope, then maybe like a roller coaster, because it goes up slow and then starts going down fast.
Okay, but is that going to be the same slope? So maybe the rate that a roller coaster is falling? So not the whole thing, because it's not going to go up and down at the same rate, right? So the rate that a roller coaster falls, would that be an example or a non-example? An example. Rate that a roller coaster Falls. Miss Amy, what do you got? Math? Ooh, yes, a mass. So would mass be an example or a non-example? So what about mass? Like a constant weight gain or a constant weight loss? No, I like it. A constant weight gain or loss. What about money in a savings account? Is that linear or nonlinear? It depends, right? So let's say that it's a bank account, a savings account that, does it increase the same amount every month, or is the bank going to give you the same amount back every month? No, because it depends on how much money you have in the bank, right? So I'm going to say that's nonlinear. So that's a non-example. So I'm going to say amounts in a savings account. What we got? I saw another hand. Ooh, yes. So would that be an example or a non-example? Example, because it's a constant rate, right? So your rate of pay, so amount of money in a paycheck. Perfect. Amounts of money in a paycheck. What else we got? Ooh, car payments. So would that be an example or a non-example? Yeah? It would be. Okay. I ran out of room, but if y'all have more space. Car payments. All right. Yes, ma'am. Yes, go right ahead. All right. If you would, please, let's glue this into our notebooks. Oh, I almost glued it into the wrong notebook. Let's glue this into our notebooks. I'm going to title this page. You're welcome to go get some if the cabinet's unlocked. It's on the right side, almost eye level. Like, look down just a little bit. All right, so I'm going to title my notes here, Linear Functions. Linear functions. Did you find it? Fantastic. And I'm just going to put a little bit of glue at each corner. A dot there in the middle. Let's see, what do I want at the top? I'm going to put graphs at the top. It doesn't matter which one goes at the top because you'll be able to see them all, right? Because you can unfold them. Oh, look how pretty. And they can fold back. All right. Tonight's homework, you guys, we're going to review for our test on Wednesday. So I'm going to hand out your review. That's going to be your homework tonight.